All right, let's try this, guys. Hello, everybody. So I'm going to try to record this PowerPoint in the same fashion that we would have been doing the inquiry demo and rotation. So please make sure, let me click on the second slide, that you have this document. So you would have gotten it from class. If you don't have one, let me know and I will post it on Schoology, and it might already be there. But you need that document where we should already have questions 1 through 6 covered. I know we still need to finish the right side of number 2, the chart on rotational motion, and there will be a later slide. So don't worry about doing that now. So pause right now if you need to go get that sheet and a pencil, and then come back to this. Throughout this whole presentation, you can pause and rewatch or rewind as needed. And then I will be asking some questions as well. So please write down the answers to those because I'll look to see that you did. And then we'll submit this demo on Schoology. I'm hoping as we try this and do this that, I will have enough visuals and practice that you still get to get the information in different ways. And then we'll find a way to practice information in various ways and then assess. So just be flexible, but I don't want to change the flow too much. So hopefully it will be similar to what we've been doing. And then I'm also thinking about doing a conference call, like a video, conference once a week maybe. Just we can do live bell work questions, practice questions, that kind of thing. So I'm thinking Friday maybe, but I'll get back to you with more on that. All right, so if we're ready, let's keep going. So questions 1 through 6, I think both classes finished. So just double check that they're filled in. And then flip the page. There was supposed to be questions 7 through 11 on page 2, but that didn't print out. So that's okay. You're going to just write those as I'm speaking and telling you how to fill them in. And then you can just handwrite the questions and we'll still submit it. So it's no problem. So as you flip the page, number the next question 7 by hand. And the question was, after we predicted, and some of you predicted that the disc will go down the incline first, others predicted the ring, and I think there was a few same answers. So we're going to run it. I'm going to show you a video of what actually happened. So for question 7, you're going to record your observation. So here it is on this slide. It is, let me pause here for a second. Play the video, and it's already in slow motion, so you should be able to play it, rewind it as needed, and see who won. Record that for question 7. Here it is. Okay, so there's your answer. Question 8. Please pause the PowerPoint at this point, and under number 8, write down some hypotheses of why you think the object that got down the incline won. List all the testable factors. So think about what is the difference. I can tell you as a reminder that the two original objects, the disc and the ring, are the same size, same diameter, and the same mass. One is metal and one is wooden. So think of any factors that would affect their rate of rotation or their angular velocity. That's that little w, right? So one of them obviously rotated faster than the other. So what do you think the cause of that may be that we could test? So pause here and fill in your number 8. Question 9. So again, put number 9 on your blank sheet. And let's see how many of the factors we can test. So you could have listed anything from material, mass distribution, air resistance, friction, etc. And we can't test all of them, but we can test some of them. Remember that air resistance, for example, depends on size and speed. So the lighter objects get affected by air resistance first, and therefore would be slower, right? Material will have different friction purposes, of course, so we'll look at that. And mass distributions of where the mass is would be the same regardless of size and mass. So let's see, as you're watching the next set of clips, again, feel free to pause and rewind as needed. I want you to look at the clip, see what factor we can be possibly testing there, and record what your result was of your observation. So here's clip 1 for the factors. So in this case, we have our original disc with a tiny little ring that's made out of plastic. So we're changing their different masses. Right? One is much lighter than the other. We also changed material. It's now very, very light plastic. And the disc is still wooden. But we are keeping the same mass distribution where the mass is for each object. So we'll play it. Again, pause and rewind as needed. And see who won and record that. Right? When we changed these factors, what was the result? Right? Let's go to clip 2. Clip 2, notice we switched the objects, so we went back to the original ring, but now a very small disc. So again, we changed the mass, we changed the material back to metal and wood, and we kept the same mass distribution. So let's see what happens here. Again, pause as needed. Okay, record your observations there. Clip 3, we have 2 rings that are going to go against each other, so the little plastic ring and the little metal ring. Pause as needed. So question 10, still on the blank sheet. What does the rate of rotation depend on? So far, anything we have changed did not change your result, and the disc always won. So it doesn't seem to matter what mass it is, what size it is, or what material it's in. The only factor that we can see is the mass distribution. So the answer for 10, what does angular velocity depend on, or the rate of rotation? And that depends on mass distribution from the axis of rotation. More on that in the next question. Let me repeat that. It depends on mass distribution from the axis of rotation. Pause and record that for question 10. And if you notice, the ring, we might say, is all concentrated with its mass on the outside, where the disc is a little bit more spread out. So what do we mean by mass distribution? We'll cover that a little bit. But first, for question 11, which should be the bottom of that blank page, is asking you to define the axis of rotation. Axis of rotation, here's your definition. It is an imaginary line around which the object is trying to rotate. Once again, axis of rotation is an imaginary line around which the object, or the average mass distribution of the object, is trying to rotate. So that's question 11, and that should be at the bottom of your page 2. Pause here if needed. Look at the picture. It's showing you 6 different objects with various axes of rotation. For example, the first one, if you have a stick that's rotating horizontally, the axis of rotation is vertically through the middle. If you put that disc or cylinder straight up, it will be a line going straight through the middle, parallel to the rest of the object. If it's a sphere, it will go through the middle, potentially. And if it's a square or a flat object, you can put it anywhere, middle or in the corner, right? So it's an imaginary line around which the object on average will try to rotate. So what does it mean on average? So please look at the first picture, top left. It's a stick that's rotating around its center of mass. Axis of rotation has nothing to do with center of mass. Let me say that again. Axis of rotation has nothing to do with center of mass. Sometimes it goes through it, and other times it won't. So if you look at the top left picture, from that imaginary line, if we measure all of your distances to one side of it, it will average exactly in the middle between the axis of rotation and the edge because it's a symmetrical object. Let me know if that makes sense. So if this stick is 50 centimeters long, axis of rotation would be at 25 centimeters, right? And the average mass distribution from 25 centimeters would be then halfway out, right? So 25 divided by 2, 12.5 centimeters from the axis of rotation. So the average mass distribution of a stick that is 50 centimeters rotating around a center of mass axis of rotation that is perpendicular will average 12.5 centimeters from the axis of rotation. Okay, we'll do more with that, but I just want to make sure you're seeing what I'm talking about. Question 12. Now you can flip to page 3, and now you have those questions printed. So this is a checkpoint question. Think about the Newton's laws of motion pertaining to linear objects, or translational, just to make sure we use the terms. And how could you tweak your understanding, which is similar, for rotational motion? So here's the question that is under number 12. Let's say we allow these objects, the original objects, so we're going back to the disc and the ring, we let them get down the incline and then let them continue rolling straight on a friction surface. Which object will stop first and why? So let's assume they have the same friction on them. So when they are rolling horizontally, which of those two objects will stop first and why? Pause here and answer question 12. Question 13. How hard is it to change objects' linear motion? So this should be a review, hopefully. We need to define linear inertia. How hard is it to change your linear motion? So the first thing we need to remember, inertia is defined as resistance to change your motion. More specifically, it's your center of mass's resistance to change its motion. It depends on, still part of the definition for 13a, depends on the mass of the object. So for 13a, you should have two things. One, the definition, which is the center of mass's resistance to change its linear motion. It depends on its mass in kilograms. So 13b, we measured in kilograms. The more kilograms you have, the more resistance you have. Now, reminder, that works both ways. A big object is really hard to get moving. It will require a lot of force. However, once we get it going, a big moving object is really hard to stop. It has a lot of momentum, it has a lot of resistance. So it's harder to move and harder to stop. When the resistance is high, it's high in both ends. So for question 14, to help us review again how we overcome the inertia, we do that. So we'll tweak that for number 15 on how we overcome. 14, we're just paralleling. How hard is it to change an object's rotational motion? Right, so linear motion, inertia. What about rotation, the state of rotational motion? It depends on what's called moment of inertia. So as opposed to inertia, we are talking about the moment of inertia. Now here's why the word moment exists. As we mentioned earlier, depending on how you rotate your object, your axis of rotation changes. So you can flip it around the corner, around the end, around the middle. Since there's different ways to rotate you, that's the moment. So what moment of rotation you're talking about? So defined moment of inertia. How hard is it to resist changes in your rotational motion? Definition, number 1, moment of inertia is resistance to change your rotational state. Moment of inertia or rotational inertia, they're synonymous. How hard is it to change your rotational state? Number 2, still for 14a, it depends on mass distribution. It depends on mass distribution. So not how much mass, but where it is from the axis of rotation. And 14b, it's measured in kilograms meters squared, or mass times radius squared. So kgm squared. Where is the average mass? What distance from the axis of rotation? So the higher the moment of inertia, the higher the resistance, which means it's hard to get that object rolling or rotating, but once it's rotating, it's really hard to stop. So in our original demonstration, we had the disc and the ring racing down the incline. The disc won because it had lower moment of inertia or less resistance. While it's rolling, the axis of rotation would be horizontally straight through the middle, piercing its center of mass. From that axis, if we measure the average distance of mass distribution of the disc, it will be halfway between the edge and its middle. That particular disc has a radius of 6 centimeters, which means for the disc, the average mass distribution is 3 centimeters from its axis of rotation. You might want to draw that out if that's confusing, right? But it's the average distance, which means if we measure from the center, the disc is evenly distributed. So some of its mass is closer than 3 centimeters, and some of it is further, right? So it's halfway between the middle of the ring, or the disc in this case, to the outside. So it has a lower moment of inertia or lower resistance to rotation because its mass is closer to the axis of rotation. The ring has the same axis of rotation in this moment, or this case, which is horizontally through the middle. However, all of its mass is concentrated further from the axis of rotation, or at 6 centimeters, because it's all on the edge. So the further your mass is from the axis of rotation, the more resistance you have. So to answer your question 12, check your answer. The ring is harder to get going. However, once it's rolling, the ring will be harder to stop. Okay, and we'll have some checkpoint questions on this on Friday, just to make sure we got this much. So the ring will be harder to stop, and therefore the disc will stop first. Because once objects are moving, or once they're rotating, they maintain their high or low resistance to change. So, question 15, how do we change our linear motion? Well, that should hopefully be a review. What causes changes to linear motion? A force. Force is measured in newtons and found by a good old Newton's second law, F equals ma. Like, that's how we find force. So linear motion is caused by forces in newtons, found by F equals ma, and measured in newtons. So what causes rotation? Remember, we do not use any linear answers for anything rotational. So forces cannot cause any rotation. If I apply just a force to either the ring or the disc, no matter what orientation they're in, they will simply slide forward. They cannot rotate with just a force. So if I want them to roll, I need to apply torque. T-O-R-Q-U-E. Rotational motion is caused by torque. Torque is found by, and it's a little Greek letter T, it's a little squiggly, but it's on your gold sheet. Okay, torque is found by force times distance or radius. So T is equal to F times R. The radius, you may want to add or clarify, it's where the force is applied from the axis of rotation. And there'll be more on this in a later PowerPoint. So force times its distance from the axis of rotation. And it's measured in Newton meters. Force, radius, Nm, Newton meters. The more torque you have, the more rotation it will cause. So here is your question 17. I'm going to show you 3 cases of rotation for each ring. You're going to pause this PowerPoint, and I want you to rank the moment of inertia of each of the cases that the ring is spinning from highest to lowest. The first thing you need to do whenever you have any rotational questions, any, from now on for this entire unit, is where is the axis of rotation. So for each case, as you're watching, pause and identify where the axis of rotation is. Okay, let's play it.
Okay, here are your 3 cases. I want you to guess or rank the moment of inertia, highest to lowest. So, case 1, case 2, case 3. One time. Case 1, case 2, case 3.
Okay, excuse the baby in the background. She was assisting. So pause here. I want you to identify the axis of rotation. Where is that imaginary line when the ring rolls as case 1? Where is the imaginary line around which the ring tries to roll or rotate in case 2? And where is the axis of rotation as the ring tips, right, or rotates downward in case 3? Answer the question before you hit the next slide. Okay, let's see how. At this point, I want to make sure you go back to the front page. Review all of the vocab that is listed for you. So far, we've went over what is the rate of rotation, or the W, angular velocity. What is the axis of rotation? What is the moment of inertia? What is torque? And the lever arm distance is the radius at which a force is applied that causes torque. Again, more on that to come. Please also make sure that number 2, both sides of the chart are filled out. And here's a closer picture, so you can pause here and fill that out. And when you're done, continue to the next slide. So we mentioned that the moment of inertia for any object depends on its moment. How are you rotating it? Where's the axis of rotation? And how far is your mass distributed from the axis of rotation? So here's a chart for common objects, and you can see, for example, a pendulum, or like a bowling ball, swinging from the ceiling, has a resistance or moment of inertia, which is measured by capital I, as mr squared. Where the mass is in kilograms, how far is that mass distributed from the axis of rotation squared. If I take the ring or the hoop and I roll it around its center axis, it would also have a resistance measured in mr squared. However, so that was case 1 in the one we just did. Case 2 with the ring that we just did was the hoop about the diameter. And as you see here in this equation, that becomes half over its moment of inertia, which means it's twice as difficult to rotate the ring around its center than it is around the diameter. So it has a much higher resistance when it's rolling around its center. Then we have a stick that we can tip or roll around its end versus around its middle. So it has, again, different resistance. Solid cylinder or a disc has a resistance of half of mr squared around the center axis. And you can see, again, the different ways that we can rotate it. If it's a sphere and it's round, you will have 2/5 of the resistance of mr squared. So here are some checkpoint questions to see if you understand and if this makes sense. So you're going to flip to the back of page 3, which is blank, and you're going to answer some of these questions that we have coming up. The first question I want you to answer, you're going to pause here and answer this question. If we were to roll a basketball and a bowling ball, regardless of their size or mass, down the incline, who will win and get down to the bottom first, and why? Please pause here and answer the question in your own words. Let's check your prediction. Please, under your answer, tell me if you were correct. Put a little check point or smiley face. If it's incorrect, please correct it and tell me why you got it wrong. What did you miss? The correct answer is the baby was excited. The bowling ball wins because its mass distribution is closer to its axis of rotation. The closer you are, the easier you are to change. Here's a checkpoint question 2. Please pause here. You have a chart that is on the previous 2 slides about different moments of inertia. It's also on the next slide here. Please use those 2 slides of all of your different moments of inertia, and I want you to record your prediction in the order of who will get down the incline first, and then second, third, fourth, and fifth between these 5 objects. Their descriptions are on the slide, top right. So please predict how they will rank down the incline. Again, please check against this chart, and if your prediction makes sense, whoever has the lowest resistance will roll faster. All right, let's check your prediction. Same rule apply. Please tell me if you are correct, and if you are incorrect, tell me why. And you can pause this and do a little slow motion and just drag it a little slower so you can see which object right before the finish line, how they rank. Feel free to pause as needed. All right, when you correctly insert the slide, your last question is your exit question that I'd like you to answer on the back of page 4, and I will grade it when you submit it. And it's really more for your feedback. I just want to see if you understand it. All right, here we go. Your exit question.
Here's your exit question. I would like you to give me the radius for the moment of inertia of this ruler in 3 ways. Okay. Rotation 1, identify the axis of rotation and the average mass distribution distance. The ruler is 2.5 centimeters wide. Case 2, you can also think of it this way. And case 3.
All right, submit this paper into Schoology, and hopefully that made sense. How you did. So I'm going to explain between the first 2 cases where the axis of rotation is and how far is the mass distribution. So first let me say the axis of rotations. For case 1, it's horizontally through the middle of the ring. So where is mass distributed? All the way on the edge, or 6 centimeters of the radius of the ring. The second case, the axis of rotation is vertical, going straight up and down through the center of mass. And that's the line around which the ring is trying to rotate. If you measure distance to each part of the ring from that vertical line, some of it will be at 6 centimeters, others will be at 1 centimeter, 2 centimeter, 3 centimeter, and every distance in between, which means it will average about 3 centimeters from the axis. The third case, the axis of rotation is horizontal at the bottom of the ring, because imagine a full circle. If it could go all the way around, it would go around the bottom. So where's the average of the mass from that axis of rotation? Let's watch.
Alright, here are the answers. Since moment of inertia has to do with distance from the axis of rotation, the axis of rotation in case 1 is right in the middle, and the average mass is going to be the radius, in this case 6 centimeters, or the radius of the circle. In case 2, the axis of rotation is actually going straight up and down the middle this way. So the axis of rotation is vertical, and the average distance is the green line with 3 centimeters. So it is half as hard to rotate it this way than it is this way.
All right, let me know if there are more questions on this, otherwise we'll go on.